I'm doing a change. Okay. Is that right, Constantina?
Yes, it's fine. Okay, so I think we can start the webinar. Once again, welcome to today's webinar organized by the WMO Barcelona DAST Regional Center. Today's speaker is Jasper Kok. And as always, during the presentation, you can use the Q&A box, the questions and answer box, to submit your questions to the speaker. Today's session is chaired by Carlos Perez and Stelios Kazadzis. So I'll give the floor to Carlos to present our speaker.
Thank you very much, Constantina. So welcome everybody to the Regional Center webinar this week. We have the pleasure of having today Jasper Kok, who's a well-known expert on DAST and other topics. And just to give you a brief overview of his career, Jasper was born in the Netherlands, and then he moved for a PhD to the US. He's currently now full professor at UCLA, after obtaining many different fellowships. And he was also obtaining like the NSF Career Award in 2016, and in 2019 the American Meteorological Society Henry Houghton Early Career Award for novel approaches to study the physics of dust emissions into the atmosphere and interactions of dust aerosols with the Earth's climate and beyond. So I'm very happy that Jasper is joining our seminars. I admire personally his work a lot, and today he's going to provide an overview on his work on coarse particles and their importance for the Earth system. So I give you the floor, Jasper. Thank you very much.
Thanks, Carlos, for the wonderful introduction, and thanks everyone for inviting me and having me here. Let's see, it looks like I can share my screen. Oh, here it is. Okay, great. So 1 second while I pull it up. Okay, so everybody can hear me fine and see the screen?
Yes.
Excellent. Okay, great. Appreciate it. Yeah, so today I'll be talking about a topic I think that has created a lot of excitement in the dust literature, shall I say, the past few years. And that is the mysterious abundance of coarse desert dust in Earth's atmosphere. It really turns out there's a lot more really coarse particles in our atmosphere than we had thought and that models account for. And we're sort of scrambling, I think, as a community to try to understand why that is and how we can fix this problem in models. Now, to first take a step back, the reason, at least for me personally, to study this topic is climate. Because aerosol radiative forcing, and I apologize if some of you have already seen this, but aerosol radiative forcing is one of the big determinants of our climate future. Together with the path that society takes, which of course we cannot really study in our field, and cloud feedbacks, it's really the radiative forcing by aerosols over the industrial period that determines our climate future. There was a really nice paper on this by Mehmet Andre about 2 decades ago now, pointing this out quite eloquently, that a model that has a strong aerosol cooling effect in which a lot of the greenhouse warming has been masked over the industrial period, and thus a small net forcing produces a large temperature increase, that under those circumstances you get a very strong temperature increase by the end of the century. And if you assume no aerosol cooling, you get about 1/3 of that. And those uncertainties of course have come down slightly, although not as much as we'd all like. But it's really aerosol forcing that one of the things we need to nail down to get a better handle on future global and regional climate changes. Now, of course, this was summarized in the IPCC assessment report last year. This is the newest iconic radiative forcing graph. You might have seen previous iterations of this. And this summarizes why we study aerosols in so much detail. We understand the greenhouse gases relatively well, uncertainties are small. But it's really the aerosols where the error bars are very large. And most of the total uncertainty in radiative forcing, which is a really strong determinant of climate sensitivity, as I mentioned, comes from the aerosols. And to my dismay, personally, dust was removed from this graph relative to previous graphs. And I think that is kind of a mistake. So on here we have sulfate, organic carbon, black carbon, ammonia, but not dust. Why not dust? Well, that's a little bit confusing because dust, we know, has increased strongly since pre-industrial times. So there's every reason to assume that it has exerted a radiative forcing. We just don't quite know what it is at this point, as I'll talk about a little bit. But we know from deposition records, deposition records tend to show increases in dust since the pre-industrial period. This is from a really nice paper by James Hooper and Karl Marx in 2018, surveying the literature on this and compiling a few dozen deposition cores, finding that most of these cores indeed show an increase in dust. The most dramatic of these, perhaps, is from a nice paper in Nature 2010 by Mulitsa et al. And this is a core here right off the coast of the Western Sahel, and showing this rather dramatic increase in inferred dust flux that they think coincides with the rise of industrialized agriculture. So linking it to human land use changes, although changes in climate, either natural or forced, can also play a role in this. And I'm working on a paper on this myself. I'll show a result of in the next slide right here. Okay, so we know dust has very likely increased quite substantially. But the problem is that models do not capture this. Models are not, in general, are not sensitive enough to dust. This is from, so the vertical axis here is a relative change in global dust loading since the pre-industrial period. The black here is from a reconstruction I'm doing. That's, I'm hoping to submit this paper in the next month or two. But this is in line with what others have found, like a study by Natalie Mahowald 2010 and the study I just mentioned, who actually find even larger increases in dust. And the CMIP6 models, this is 7, there's 5 more that show the same thing, basically get a flat response, don't really show any change in dust. They're not responsive enough. And that's a well-known problem with dust models. And so this raises the possibility, dust has increased a lot. We know that it produces all sorts of impacts on the Earth system. Are we missing a possibly substantial radiative forcing of dust that is overlooked both by the climate models and by these IPCC assessment reports? So we need to figure that out. We need to figure out what is the direct radiative effect of dust through interactions with radiation, and what's the indirect effect through interactions with clouds, biogeochemistry, atmospheric chemistry. And those interactions depend really strongly on the size of dust, with fine dust generally producing cooling and coarse dust generally producing warming. This is especially well understood for the direct radiative effect, so the direct scattering and absorption of radiation, where we know fine dust tends to cool. And here I put the boundary between fine and coarse at roughly 5 microns in diameter. Now, because a scattering tends to scale with surface area, the finer the particle, the more scattering, and the coarser, the more absorption, because absorption tends to scale with volume. And so fine dust tends to cool, and coarse dust tends to warm, not only by absorbing shortwave, but also because coarse dust is large enough, it can interact with long wave radiation, much like a greenhouse gas does, and so produce a warming effect in that way. A few years ago, we looked into this. This is from a paper in 2017. So the vertical axis here is the global dust direct radiative effect at top of atmosphere. These are results from the AeroCom phase 1 model, this ensemble of aerosol models. And these generally found, a strong shortwave cooling effect offset by some long wave warming for about a -0.5 watt per meter squared top of atmosphere cooling. Now, since then, we've learned that these models had too much fine dust and not enough coarse dust, as shown in this figure. And I'll show a lot of plots like this, where the vertical axis is the size distribution of dust, so mass, in this case, mass per logarithmically spaced bin, versus the geometric diameter of dust. And geometric diameter meaning the volume equivalent diameter. So if you take the spherical dust particle and squish it into a sphere, it's the diameter of that sphere. And so the shaded area here is a constraint based on what we measure at emission of the size distribution and what we simulate from an ensemble of models of how long these particles stay in the atmosphere. And from those constraints, all models underestimate coarse dust and overestimate fine dust. So we've corrected that and that, of course, yields less short-wave cooling, more long-wave warming, and a weaker top of atmosphere global radiative effect. That's not the end of the story, because since then, of course, we found out there's even more coarse dust, as I'll get to in a second. But this sort of this dichotomy between fine and coarse dust also exists with other interactions. So interactions with clouds. With warm clouds, the fine dust tends to act as cloud condensation nuclei, much like anthropogenic aerosols can, and therefore add to the indirect cloud effects that produce a cooling effect on climate, extending the lifetime of clouds and increasing their albedo. But coarse dust has the opposite effect, because these particles are so large that they, when they're activated in clouds, they can absorb so much water that they draw down the supersaturation quickly, and therefore prevent the activation of anthropogenic cloud condensation nuclei, so counteracting the effect of anthropogenic cloud condensation nuclei, and thereby thus producing a warming effect. And this is, I would say, severely understudied. There's not many studies on this, but those that do exist indicates this could be quite a substantial warming effect. But with these complicated interactions, we really need a lot more study. Another really main effect of dust on the climate system is through its role as the atmosphere's main ice nucleating particle, which affects mixed phase clouds and especially cirrus clouds. These are really, really complicated interactions. I won't get into much detail, but current understanding is that these probably produce a net cooling in the global average. All right, so the main point I want you to take away from this is, one, dust is increased. Two, models do not represent this, and that might be missing a radiative forcing from dust. And three, what that radiative forcing is really depends on the balance between fine dust, which cools, generally speaking, and coarse dust, which warms, generally speaking. Okay, so with that background, so in the past few years, there's been several lines of relatively independent evidence that models, despite the adjustment we've already made, still greatly underestimate the abundance of coarse dust in our atmosphere. And there was a really nice paper on this by Albert Ansman and colleagues, where they did a cruise across the tropical North Atlantic and used a lidar that can separate between fine and coarse dust. And that's shown here. This is the measurement at Cape Verde. So black here is the coarse dust as measured or observed really by a lidar. And red is what an ensemble of models predicts, including the Barcelona model here. So you can see here already, the models do not have enough coarse dust. And now if you do the same, so this is model, this is observation. If you do the same comparison at Barbados, you can see that disagreement gets worse. So here, the model is even further underestimating the coarse dust by about an order of magnitude. So clear problem there. There was, from that same field campaign, a really nice Lagrangian style measurement where they measured approximately the same dust plume in Cape Verde and Barbados as well. So here again, this is size distribution. The vertical axis here is number per logarithmically spaced bin. The blue is what you have at Cape Verde. And then just from gravitational settling, you would expect everything larger than this dashed line to fall out. But when you measure at Barbados, a lot of those particles are still there. So, there's something going on here that models are not definitely not reproducing. And then from my own group's work, we looked at in situ measurements, so aircraft measurements of coarse dust. So again, this is a normalized size distribution, this time volume per logarithmically spaced bin. We normalize it at both at 1, so models and measurements at 1 at 5 microns to emphasize the discrepancy or the agreement or disagreement for coarse particles. And you can see there's a very large underestimation. This is from an ensemble of 6 different models, chemical transport and climate models. And this against the measurement from Claire Ryder and colleagues. And now if you look at all the measurements we can find, 22 in total that met quality control criteria, we can see that this happens for every one of those 22 measurements. So for every one of those 22 in situ measurements, and you can see their locations here, there's an underestimation and sometimes an orders of magnitude underestimation of the coarse dust in the atmosphere, so indicating a clear problem. Okay, so with that then, let's talk about the questions I'm going to try to answer in this seminar. So first, I'm going to figure out, okay, how much coarse dust do we think is actually missing from global models? How big of a problem is this? And then what's the direct radiative effect that this coarse dust contributes that we are currently missing in models? And then, of course, the big question is, okay, how come models underestimate this so much? You know, what's causing this? And roughly speaking, there's two possible causes. One is that models underestimate the emission flux, that there's more coarse dust being emitted than models account for. And I'll derive a new parameterization for the emitted size distribution that accounts explicitly for this coarse dust. And the other option, of course, is that models overestimate coarse dust deposition. And the answer with most things is it's a combination of those two. Models both underestimate emission and overestimate coarse dust deposition, as I'll show you. Okay, so first, how much coarse dust is missing from global models? So we approach that problem from this ensemble of simulations of the three-dimensional size distribution of dust, and the models are written out here. And this compilation of in situ measurements. We have 22 in situ measurements of the size distribution of dust. And so then we figure out for each model, okay, by what factor do we need to multiply each particle bin in the model in order to minimize the disagreement with the models. And so from that, we correct essentially the model simulations, the size distributions that the models simulate, and we get a constraint on the three-dimensional atmospheric dust size distribution, in which we propagate the uncertainties from the measurements and the spread in the model ensemble using a bootstrap procedure with resampling. And so I showed you the left here already. These are the 22 measurements. And so with this procedure, by design, of course, we get much better agreement, the red line here, against the measurements. The right here is the log mean bias. So the mean bias between this model ensemble and the measurements into three particle bins here. And this is a log scale. So this minus 1.4 for the 10 to 20 micron bins, that's 10 to the minus 1.4, 10 to the 1.4. So this is a factor of 20 or so. So it's a really, really large underestimation of coarse dust here. And by design, that bias is eliminated through this procedure. And we end up with basically an unbiased 3D size distribution, at least against these measurements. So from that, we can now integrate over the entire globe and figure out, okay, how much coarse dust is in the atmosphere. And that's what we get here. So this is, again, I promised you lots of graphs like this. This is the mass distribution in mass per logarithmically spaced bin versus diameter. The black line is what we obtained previously in that paper I showed you before, where we constrained the radiative effect. And that was already a correction, right, to basically saying models need to have more coarse dust. So it turns out there's even more coarse dust. So the red line is what we get from this constraint, just using models and in situ measurements, getting a lot more of this coarse and supercoarse dust than models predict. So if we now add all that up, we find that the atmosphere contains, a fairly astounding 17 teragrams of coarse dust. 17 teragrams. And if we now look at what's in models, and this is from Aerocom phase 1 models, which was the latest ensemble of Aerocom that was analyzed in detail at the time. And of course, since then there have been newer models. These models all, of course, underestimate the coarse dust, and quite substantially in most cases. So these models account for only about 4 teragrams of this coarse dust. So they're either directly omitting by not extending the diameter range that's simulated to coarser sizes, or underestimating if they do simulate that, and capture only around a quarter of the coarse dust in the atmosphere. So yeah, it's quite a lot of coarse dust. And so it's worth pointing out here, the total load of particulate matter in the atmosphere is something like 50 teragrams, of which more than half is dust. So models are missing around a third or a quarter of that particulate matter load. So it's quite substantial. Okay, so what then is this important? What is the actual radiative effect of the missing dust, missing coarse dust, and the direct radiative effect? So to get that, we extended our methodology here. So we already have a constraint on the three-dimensional size distribution. And then we fold in constraints on extinction efficiency. So we get then the global optical depth that is produced by each particle size. And we combine that with model estimations, so an ensemble of model estimations of what the top of atmosphere direct radiative effect is per unit of extinction at a given particle size. So per unit of dust aerosol optical depth globally integrated as a function of particle size. And from that, we can estimate the global top of atmosphere direct radiative effect. And so that's what we see here. So the vertical is that direct radiative effect for coarse dust. And so we find it's around 0.2 watts per square meter for this coarse dust. And of course, that's around 4 times what AERCOM models have, which have only about 0.05. So we find that these models are missing around 0.15 watts per square meter of this direct radiative effect, which is quite a substantial fraction of the total direct radiative effect of dust, which is shown here. Because so this is fine dust, and when you add coarse dust, that means that the coarse dust is accounting for part of the observed dust aerosol optical depth. So you need less fine dust to explain the rest. And so you also reduce the cooling you get from the fine dust. So overall, you get a radiative effect that's closer to zero, and we can't really tell at this point whether dust warms or cools. The uncertainties here are vast, and that's in large part because of uncertainties in optical properties, especially in the shortwave, where models diverge widely, like a factor of 5 or so, in what the shortwave cooling is, in large part because of uncertainties in the optical properties. So that's a clear area that needs more research. Okay, so we've established, at least based on my work, that models are missing a lot of coarse dust, that this is radiatively important. So we need to try to fix this. So how can we fix this? Now, to do that, we need to understand, okay, what the problem is. So first, let's look at if the problem is an underestimation of coarse dust emission, and if so, if you can do better with an improved parameterization. So this is what's in current models. So here the vertical axis again is the size distribution. This is normalized, meaning that if we integrate up until 20 microns, we get 1 over these size distributions. So these are parameterizations for the size distribution of emitted dust aerosols that are in models. This line, the dotted line, is my own past work in 2011, and these are other parameterizations that are in models. If we now, by Charlie Zender and Yves Balkanski, and if we now add measurements, so these are measurements of ground-based measurements where people go into actively eroding fields or dust storms, measure the dust concentration at several heights, and from that infer what the dust flux is, size resolved, that is being emitted by the surface. And so this is from 10 different studies, and you can see here that all these parameterizations, including my own past work, underestimate substantially the coarse dust. Another thing you can notice here is we don't have all that many measurements. There's really only 2 studies here that provide much information, and that's because it's really, really hard to measure coarse dust, because particles with that much inertia are really difficult to sample accurately, because they tend to bang into inlets basically because of their inertia, and so it's actually really hard to measure. I'll return to that point. So yeah, but models underestimate the emitted coarse dust, even from the field measurements we have. We can look now also at in situ measurements where we don't have the inlet problem, because there you can take measurements without using an inlet that basically causes the coarse particles to not be sampled because of their high inertia. So this is from measurements by Claire Ryder and colleagues. That's the magenta line here. This is low in the boundary layer. during the daytime, so freshly uplifted dust in Mali and Mauritania. So that's the magenta, and you can see that this is an ensemble of models again, that same ensemble. You can see there's a clear underestimation that happens when you get to coarse particle sizes here. So we see the same thing from emitted measurements and from in situ measurements. All right, so we can fix this, right? We know that models underestimate the emitted emitted coarse dust. So let's try to develop a new parameterization that accounts for this very large abundance of coarse particles at emission. And now for that, we need to, of course, look at the physical process by which dust is being emitted. And that, of course, is this process of saltation, the bouncing motion of sand grains. And these sand grains are massive, hundreds of microns, and they smack into the soil. And that can, cause aggregates of dust in the soil to fragment and produce dust aerosols. So a really key point here is that small particles in soils tend to organize into aggregates. This is a really pretty picture of that. And so when these sand particles, whack these aggregates, what happens is you have this aggregate of particles. You put impact energy into it, and if that impact energy is sufficient, then the aggregate will fragment, right? And so you get a number of different fragments. And so the question then is, what is the final state of that aggregate? Does it indeed fragment? And if so, into what particle sizes? And if we know that, then we have a good handle on the size distribution of what is being emitted from the soil. Now, of course, that problem is kind of a nightmare to solve because these particles are all different sizes, different shapes, different mineralities, different bonding energies, with which they're sort of glued together, with weak bonds or stronger bonds. And so solving that sort of problem from first principles, would probably be decades of work, and might even be unsatisfactory after that. So instead of trying that, we looked at the closest analog problem in physics that we do understand, at least somewhat, and that is the fragmentation of brittle materials like glass. Because what happens when you have that aggregate of soil particles that are all bonded together, and that gets whacked by the saltator particle, is really very similar from a physics perspective of what happens when you say take a wine glass or something, you throw it on your kitchen floor. Now, not to be recommended, but it's a good analogy for dust emission. Because in both cases, you have a brittle material, the aggregate of dust particles on the one hand, and the wine glass on the other hand, that receives impact energy, and that impact energy creates cracks in the material. Those cracks propagate through the material and they merge, and that's where the fragments come from, right? And in the case of the dust aggregate, those cracks would propagate along the boundaries of the pre-existing particles, right? It wouldn't create new particles. It would just choose the path of least resistance. And something really beautiful happens in nature for brittle material fragmentation, and that is a scale invariant process. In other words, there's no dominant length scale that determines the interaction, and therefore you get a power law. And this happens in all sorts of processes in nature where you don't have a dominant length scale. Things like sizes of clouds, sizes of asteroids, magnitudes of earthquakes are all scale invariant processes for that same reason, that there's not a dominant length scale determining the interaction. So if you take that wine glass, you throw it on your kitchen floor, and you count down meticulously all the little fragments and measure them and put them on a graph, you should get something like this. So here's fragment size versus, again, the size distribution, number of particles per logarithmically spaced bin, and you get these beautiful straight lines, power laws, because this is a logarithmic plot. And not only are these power laws, these are really nice, well-behaved power laws. These are all with an exponent of -2 on this plot. So the number of particles per logarithmically spaced bin scales with the particle diameter of exactly -2. I've already mentioned that. Okay, so let's try to understand why this happens in brittle material fragmentation, and then apply this to, we need to adjust it, but then we'll apply it to the fragmentation of dust aggregates, and then see if we can account for the occurrence of so much coarse dust at emission. Okay, so what happens in brittle material fragmentation? Like I mentioned, you put impact energy, a lot of impact energy into brittle material, what happens is you'll get numerous cracks that will form in the material, and those cracks will propagate, much like if you take a piece of fabric and you start tearing it. Much like that piece of fabric that you start tearing, the more that you tear, the larger your sort of moment arm becomes, and so the stronger the stress will be at the tip of the crack. And at some point, that means that the material cannot take that stress at the tip of the crack anymore. And so it will start spitting out basically side cracks to relieve the stress at the tip of the crack. And once that happens, the stress at the tip of the crack is reset. And so it will go back to a low number, keep propagating, and keep building again as the moment arms increases until the stress again becomes too large and it emits a side crack again that offloads some of the stress. And so this process repeats, and for an impact with enough energy that is fragmenting, this will occur at approximately, not exactly, but approximately regular intervals. Now, once that happens, nature does not like free surfaces, right? It takes energy to create. So these cracks will be attracted to each other to minimize the energy that must be created in these cracks propagating. So in the first generation, these cracks are attracted to each other. And when they merge, that's when you get a fragment. Right? So these fragments will have this, typical size of L, the spacing at which these side cracks emit. So you get n over 2, where n is the number of these side cracks, n over 2 fragments of this typical size. And then in the second generation, the cracks that keep propagating, they will merge, and you get half the number of fragments with twice the size. So you can see where the power law comes in. And this keeps going and going. And so that's where the power law. And of course, this is a simplification. But if you do this in three dimensions, you get this power law of number of particles per logarithmically spaced bin, scaling with particle diameter to the power of -2. All right, but any scale invariant process can only hold for a limited size range. There's a limit on the small end and there's a limit on the large end. So for brittle material fragmentation, you cannot keep fragmenting down to the size of indivisible constituents. And so for glass or for something like gypsum, this will be the crystal unit or the molecule if there is no crystal. For a dust aggregate, this will be the size of the discrete dust particles, the discrete dust particles that make up the aggregates. Because in general, the fragmentation process will just propagate right along the boundaries of pre-existing particles. It will take the path of least resistance. It will not fragment discrete particles. Now, at the larger end of the spectrum, what limits the size is the distance between these main cracks. So this is a simplified schematic of cracks that propagate and merge in a brittle material. And so if the typical distance between main cracks is 2 lambda, then your fragments cannot be larger than lambda, right? Until it bumps into another side crack. And so you get an exponential cutoff for this. And most scale invariant processes, not all, but most have an exponential cutoff, like the magnitude of earthquakes, for instance, has an exponential cutoff that has to do with the size of the Earth. You cannot get earthquakes that, for which the magnitude requires place larger than the side of the Earth to interact. So the same thing happens for brittle material fragmentation. There's an exponential cutoff here. And this lambda, that depends on the separation between the main cracks. And that in turn depends on how large the object is. The larger the object, the larger the spacing between these main cracks will be. And the proportionality constant here is of approximately 0.1. It's not well constrained and it will depend on other factors. And so you end up with a size distribution for brittle materials that looks like this. The scale invariance with this exponential cutoff, but the exponential cutoff will depend on the size of the object that you're fragmenting. Okay, so now let's apply that to the fragmentation of soil aggregates. All right, so first, we're going to see if from the size distribution of dust as measured, if we indeed see that this is consistent with this idea that these aggregates are fragmented by fragmented by, well, are like a brittle material fragmentation process, and that is driving dust emission. So here, what's plotted is those 10 studies in the range in which we would expect brittle material fragmentation, the scale invariance to show up. So this is diameter again versus number of particles per logarithmically spaced bin. And you can see this is a straight line. And not only is this approximately a straight line, it's exactly the straight line that we would expect. So this is the power law of -2 that we see in the fragmentation of brittle materials. So in this size range, dust emission follows approximately this brittle material fragmentation power law. What's more, if we now zoom out, for smaller sizes, the creation of smaller fragments is limited, is depleted from the power law, as we would expect, because you cannot create fragments that are smaller than the size of the discrete particles in these aggregates. So we would expect there to be depletion from the power law for smaller particles. There's also depletion at the larger end, which again we would expect because you cannot create particles that are fragments that are large compared to the size of the object being fragmented. So from that, it appears consistent with brittle material fragmentation. So with that, then we can obtain an analytical expression that accounts for those three effects, right? So the scale invariance, the depletion at small particles, and the depletion at large particles. So scale invariance is just the particle, the power law. Now, to account for the depletion at small particles, we remember that the creation of these smaller dust aerosols is limited by the availability of discrete dust particles. So in other words, if you are creating an aerosol of size 1 micron, it's the fraction of particles in the soil that is smaller than or equal than that 1 micron that contributes to the creation of that aerosol of 1 micron. So we put a term in here now that's the cumulative size distribution in the soil of fully disaggregated particles up to the aerosol diameter that's being created. Right, so it's the soil cumulative mass fraction up until the aerosol diameter that's being created, up until D. And then at the larger end, and of course, we can assume now that this is a log normal distribution, right? The size distribution of disaggregated particles in soils, which is a very good approximation. We integrate that, we get this error function. The details here don't really matter, but it's an analytical expression we can obtain where these are parameters for the size distribution of disaggregated particles in desert soils. So it does depend on the size distribution of desert soils, but these parameters, at least from our survey, don't change all that much between different soils. So to an approximation, we assume them constant, also because we don't have a lot of information on this on a global basis. And then for the larger size range, the creation of these larger aerosols is limited by the finite distance between cracks. So, and for here, this will deviate from the paper I published on this in 2011. This is the update to that. So, the size distribution from fragmenting a single soil aggregate will look like this, right? It's the exponential cutoff. And that exponential cutoff depends on the size of the aggregate. And so in a soil, there will be a wide range of aggregates, right? There will be a size distribution of aggregated particles, not to be confused with the size distribution of disaggregated particles that we used previously. But there'll be a size distribution also of aggregated particles that peaks around 100 or 200 microns or so. And so for each of those particles, when you fragment it, you get an exponential cutoff at a different point. So you need to integrate over that size distribution of aggregated particles. Now, that size distribution of aggregated particles is also log normal. Here also, we don't have a whole lot of measurements, but the measurements we do have, which are around 20 or so, find that there's no clear relation between the size of aggregated particles and soil properties, somewhat to our own surprise. But things like the fraction of clay, the fraction of silt, pH, things like that don't explain the variation in the aggregated size distribution. And in fact, the variation in aggregated, the size distribution of aggregated particles is not all that large. And I have a plot of this at the end, if anybody is interested. So we assume that constant as well, both because we cannot explain the variation, because the variation is not that large, and because we simply don't have data to describe how it varies on a global basis. Okay, so we plug all that in. So we have the scale invariance, we have accounting for the limitation of the smaller particles because of the presence of discrete particles, and we have this cutoff that varies with every aggregate that you fragment due to the limitation of the distance between main cracks. And so when we plug that in with parameters here that come from soil measurements of aggregated and disaggregated particles, we get pretty good agreement here. There's obviously scatter, especially at the fine range and also at the coarse range here. And this is what it looks like for the volume size distribution, right? So we seem to be able to explain the general trends in the data. And importantly for this talk, we are now accounting for the large abundance here of coarse dust particles that the previous sort of iteration of this theory did not. So there I did not account for the sort of the variability in the aggregates, the size of aggregates that are being fragmented. So it turns out that that's critical in explaining why there's so much coarse dust being emitted. Okay, so now let's take the next step and put this in a model and see if, including this new parameterization for the emitted size distribution that accounts for this coarse dust, if we can now indeed reproduce in situ measurements of coarse dust. And fortunately, the answer is yes. So this is what I showed you before. These are measurements that are widely used by Claire Ryder, really state-of-the-art work, and colleagues. And this is what the ensemble got before, right? These 6 different models. And now we implemented this new parameterization into the community Earth system model that my group works with. And the dashed line here is the parameterization at emission. And the blue line here is what we get when we compare against the measurements at the same time and same location. And you can see that the agreement here is quite good. But the kicker here is that it doesn't stay good, because this is at emission. This is freshly uplifted dust close to the surface, right? This is as close to being emitted dust as you can get from in situ measurements. But now if you look at dust that is aged, we see a different story. So this is aged dust from the same measurement campaign by Claire Ryder and colleagues. And very close to the surface, it's okay. You already start to see maybe there's a slight underestimation here of coarse dust. If you go higher, you start seeing that the model starts clearly underestimating coarse dust. And as you go even higher, it gets worse. So the higher the altitude, the larger the underestimation of coarse dust we get. And now if we look, and this is still over source regions, right? This is Mauritania, in the Atlas Mountains. This is in the Sahara. If we now look further afield, and I should mention this is from a paper that we have in press in Geophysical Research Letters. It's coming out hopefully soon. If you now look further afield at the Canary Islands, this is the same measurement campaign by Claire Ryder. So these measurements are very comparable to what I showed before. You see like a really clear underestimation of coarse dust. So even though we're getting the emission right, the model greatly underestimates coarse dust after transport. And we get this in comparison to other measurements as well. This is against Wagner et al. In South Portugal. This is against that field campaign I showed in the motivation at Cape Verde by Bernadette Weinzierler and others. Also a very strong underestimation. So what's happening here? Well, we don't know, but we do know that one fix for this, so to get a handle on just how strong an effect this is physically, what we did is we reduced the density of these particles by a factor of 10 and a factor of 20. And so these are the yellow and brown lines here. And now we can match approximately the measurements. So in other words, whatever process the model is missing, that's causing the dust to just deposit way too fast in the models is equivalent to reducing the density of dust by a factor of 10. So it's really a really big thing that we're missing. And very nicely, there was a really nice paper that was posted last week by Drokaki et al. on ACP that completely independently reached the same conclusion. So They did actually compared against very similar measurements also by Claire Ryder, and used a Wolfram model, and also found, okay, we need to reduce the settling speed by about a factor of 3 to 5, which is equivalent to reducing the density by about a factor of 10 to match measurements. So there's clearly something missing that transcends this individual model, it seems. Okay, so clearly models are not only underestimating coarse dust emission, they're also overestimating coarse dust deposition. So why is this? And I have some ideas for this, and others hopefully have other ideas. This is very much a matter of debate. One partial explanation, this cannot explain it fully, I think, but contributes, is that dust is, I think, much more spherical than we had previously realized, and it's enough to slow down the settling of dust. So these are some nice images. There was a nice paper on this about a decade ago, hypothesizing that this explains observations by the Calypso LiDAR instrument, where they seem to see an increase in asphericity of dust with altitude. And so when we account for this, when we take measurements of shape and calculate, making some simplification that these particles are triaxial ellipsoids with a random orientation, we find that you reduce the lifetime by around 20%. So the terminal velocity is reduced by 15%, and the lifetime is increased by 20%. So this plays some role, but it cannot explain the massive underestimations that we see with the model. Another factor might be that topography dramatically increases the vertical transport of coarse dust in the boundary layer, which we know, of course, is very deep over the Sahara, especially in summertime. This is from work led by my colleague, Marcella Ciamecchi, here at UCLA. And you can see that the existence, I love this movie, the existence of even mild topography creates vertical velocities that lift these coarse particles higher up in the boundary layer and creates a lot of turbulent dispersion in the wake of these hails that causes a lot more transport higher up into the boundary layer, enhancing the vertical transport by orders of magnitude for 60 micron particles. So this is certainly an important process, and models with coarse resolution are going to be missing a part of this. So it depends very much on resolution and how the boundary layer is parameterized in models. A third explanation that we're working on is turbulence in the Saharan air layer. There's indications that it is turbulent, often the Saharan air layer, and that would slow down the settling. And that turbulence could be generated either just by shear in the winds or by buoyancy, with shortwave warming by the dust from the bottom and longwave cooling out of the top by just dust emitting in the longwave spectrum. That's setting up a buoyant situation that could produce turbulence. And here's a very simple model for that. So if you assume at day 0, there's a well-mixed dust layer in this Saharan air layer here, with no turbulence, that would just homogeneously settle out. With turbulence, that layer would remain well-mixed, and so the flux out at the bottom would decrease over time. And so the residence time of particles would increase. And from that simple model, we get a large increase in the lifetime of dust. So this is the extreme situation with so much turbulence that it's always well mixed. So that's as much as turbulence could possibly explain. We have a detailed large eddy simulation on this that's ongoing. And I'm very close to the end here, Carlos. Great. Next slide is conclusions. So what's causing models to overestimate coarse dust deposition? The truth is, this is a good old mystery and we don't know the answer, which is always exciting. But we think asphericity plays a role. Topography might play a role in getting the particles high up in the first place. And turbulence in dusty layers might play a role in keeping them a lot further. And there's other processes that other groups I know are working on that could play a role, especially things like electrostatic forces, excessive numerical diffusion, which didn't seem to play a role in our model, but could in other models, convection events that are not resolved in the reanalysis data because of the coarse resolution, and others. Very quickly, conclusions. So we found that there's around 17 teragrams of coarse dust. This, really excitingly, is about a third of all particulate matter, and models have been largely missing this. This adds a good chunk of warming to the dust, around 0.15 watts per square meter. Models miss this because they underestimate coarse dust emission. We obtained a new parameterization for this using this analogy between dust emission and brittle material fragmentation, that dust shatters like glass. With that, we can explain measurements at emission in situ, but not after transport, and that there's clearly something else in models that's missing that is needed to be improved to explain the much lower rates of deposition. That's it. Thank you so much for listening. And I'm happy to take any questions.
Thank you very much, Jasper. We're going to have about 10 minutes for questions. So I don't know, Stelios, do you want to do it yourself? You want to start?
Yes, I can start with the first question that is coming from Mikhail Sofia. And I will just read it. He's saying that he's kind of skeptical on the numbers, mostly about the large particles, and his skepticism is about that the sedimentation of water density particles of 20 microns in diameter would be about 1 centimeter per second. So how can these dust particles of comparable size survive on a global scale?
Yeah, exactly. Yeah, no, I'm totally skeptical about that as well. Yeah, so it's really mysterious. So right, even the asphericity, right? I mean, that slows down that settling, creates more aerodynamic drag, but it's not nearly enough to explain that particles with that sort of settling speed would stay aloft. Yeah, so I totally agree. There's something really exciting going on there. I think that's keeping these particles aloft. So I don't know what it is at this point.
Okay. Then some questions about this parameterization. Probably this was partly answered, but there is also a comment about the overestimation of fine mode at 4,000 meters, and a comment about sensors with polarization sensitivity that can play a role here for these measurements of dust sphericity.
I'm sorry, I didn't quite understand. Sorry, could you repeat?
The question is that if this new parameterization also overestimates the fine mode at 4,000 meters.
The fine mode at 4,000 meters. Oh, I see. I can go back to that. Yeah, exactly. Great. Yeah, we're not quite sure why that is. Part of this is because of the way that we normalize it. We normalize it such that the integral for both the measurements and the prediction here is equal to 1 up to 20 microns. And because most of the mass is in the 10 to 20 micron range, that will be the most, or the 5 to 20 micron, that will be the most important. If we normalize this to only like 5 microns or 10 microns, you imagine moving all these lines down, then there would be agreement. So it's not really clear if this is just because if we get the coarse dust right, that this will fall into place. And we see that, of course, when we add the settling, reduce the settling, the overestimation is greatly reduced. It's still there, but it's greatly reduced. And it also depends on the measurement. These measurements don't show it. So yeah, the truth is, I don't really know if this is real, and if it's real, what's causing it. And I think there was a second question.
Yeah, there are just some comments. One is that the new satellite sensor with polarization sensitivity can be able to address this dust sphericity issue. And the second one is, electrical fields, that it's a possible, let's say, hypothesis of keeping large particles in suspension longer. You mentioned this in your last, one of your last slides. So I think this has been answered. Also, there is a question about the parameterization, but it came a little bit early, I guess, because you mentioned a lot of aspects. There is a very interesting question about this brittle fragmentation theory, if this can be applicable for other planets. For example, Mars.
I love that question. Okay, let me take the one about the depolarization. Yeah, that's very interesting. So the idea there is that, for instance, the Calypso instrument will measure the depolarization ratio, so the extent to which when you shoot polarized light at aerosols, the polarization signal is lost essentially by the aspherical particle shape. And so with that, you can quite sensitively pick up on particles that are aspherical. But the problem is that the extent to which that light is becoming depolarized is a very confusing and not sensitive function of the shape and the size. So it is almost, from my experience of reading the literature on this, it's almost impossible to use those sort of measurements to infer the extent of asphericity. You can tell whether it is aspherical or not, but there's no clear relationship between the amount of asphericity and the depolarization ratio. So from my understanding, it's really difficult from at least those depolarization ratio measurements to determine the shape and the extent of the asphericity of particles. There might be other measurements. It's not my primary field of expertise that could, but I'm not aware of them. The other question about the brittle fragmentation theory application to other planets, that's a really great question. I would love that. The closest planet for that obviously would be Mars, where we know there's a super active dust cycle. Dust on Mars is much more important than on Earth. There we don't know, I think, enough about the process by which dust is emitted to really apply this theory well, because we don't know really how what the aggregates look like. We don't really know what the discrete particles look like, but it's certainly possible that it could be applied. But I think there the uncertainties are so large that it's not really clear if it applies or not. We don't have clear measurements that could test it.
Also, there are a couple of questions. I can reunite one of them, or two of them, which is about electrical fields, electrostatic forces. If this can keep the particles up, what's your opinion about that?
Yeah, great. This is actually my PhD work a long time ago. I used to study dust electrification. And my experience is that in order to have fields large enough to keep these particles aloft, I mean, these are really, really large fields. And I think there's two problems. One is these fields would mostly need to be generated at emission when there's most of the interactions, most of the collisions between dust particles. Those charges will decay after emission because there's ions in the atmosphere that tend to neutralize charges, and so there'll be a decay time of these charges. So for me, it's hard to imagine that you would have large enough fields in the atmosphere to play a meaningful role in keeping these particles aloft. But there have not been measurements of electric fields that I'm aware of in the atmosphere. There in dust layers. There have been measurements of particle charges, and those generally have not been, I think, large enough to really explain this. But that's one problem. The other problem is that, and there were some really nice papers of this out of, there was one, Ulanovsky, 2007, and there's really nice work coming out of Vasilis Amouridis' group, that, once these particles get charged, they become aligned vertically. And now the asphericity will cause them to fall down faster because now they have less surface area, less aerodynamic drag. So it could be that it actually hurts the process, that speeds up the process. So I think it's definitely an area that needs further study, but my personal, completely biased, subjective assessment is that it's not the most likely thing that is keeping these particles aloft.
Okay, there are many questions that are happening now in the chat. I'm going to go to the Q&A still. There are two. Would paleoclimate simulations of arid periods need to be revised based on this underestimation of coarse dust?
Right. Definitely. Yeah, I definitely think so.
Okay.
Yes.
And then, I'm going to try to, because we're running out of time. So this one by Pete. Given the challenges in aerodynamically sizing coarse particles, how well reconciled are the measurements of Claire Ryder and others with optical sizing methods? And does that suggest any challenges to your overall hypothesis of an underappreciation of coarse mode dust?
Yeah, that's a really great question. So my understanding of Claire's measurements is that they're so important because they don't use an inlet. So they sample these particles in situ. So a lot of the issues with measuring the coarse dust goes away. So my understanding is that these measurements are quite reliable, also because they use several different instruments. For instance, they also use things like a cloud droplet probe, and those generally agree with each other. So of course, there's still errors, and maybe they're off by a factor of 2, maybe even a factor of 3 or 4, but they're not off by an order of magnitude, I would think. That's my assessment, not being an expert, of course, on that.
Yeah, there's also a question on if you have taken into account conversions between geometric size of the models and the type of diameters in the measurement data. This is a question by Mian Chin.
Yeah, great question. Thank you for asking that, because yes, that is an important issue. And so these measurements by Claire Ryder, we actually corrected for that. So because we have constraints on how spherical the dust is, we can calculate, for instance, using different optical techniques, when a given instrument sizes a particle, which they do based on the amount of scattered light that it receives at a certain angle, that instrument assumes a spherical particle with a certain index of refraction, and we can calculate what aspherical dust particle that would correspond to. And so we have a paper on that published last year in GRL, led by my awesome PhD student at the time, now a postdoc at Columbia, Yue Wang. And so we used that technique to correct these measurements from Claire Ryder. We did not have enough information on these other measurements by Wagner and Weinzierl to correct those measurements. So those measurements are not corrected, but the Ryder et al. Measurements are corrected for the asphericity of dust in how the instrument sizes them optically. Yeah, and that's also really important for aerodynamic measurements as well. Like the PM 2.5 and PM 10 standard measurements also are really affected by this, by the asphericity.
Okay, for the interest of time, I think we have to close here. Many people will have to leave to other meetings. There are a few questions that we will forward to you, Jasper, and I'm sure that you will be able to respond right away.
Yes.
Unfortunately, I had many questions, but I couldn't ask any of them, so I will also forward you some questions myself. So I really want to thank you for this talk. This is really a hot topic in the community, and a lot of interest is raising. So we're going to close here. Thanks again, everybody, for coming, and see you in a few weeks for the next talk, which will be performed by Maria Gonçalves on the variability of dust mineralogy in the atmosphere. Thank you very much.
Thanks, everyone.
Thank you very much.